Hi, everyone, and thank you for joining us today. My name is Robin, and I'm the product manager for the QC portfolio at Unchained Labs. I'll be your moderator, and I'm glad you've decided to join us. Before we get the seminar started, I wanted to remind any of our customers joining us today that Unchained Labs is dedicated to supporting our customers. Please do not hesitate to get in touch with your local sales specialist, application scientist, service engineer, or contact us directly at our website if you need anything. We're ready to do everything we can to help you. We will have a Q&A session at the end of the presentation. To ask questions, all you have to do is click on the Q&A button in the Zoom navigation bar at the top or bottom of your screen and type your question. We'll get to as many of them as we can. And now I'd like to introduce Lisa Krapp, one of our fantastic field application scientists. Today, Lisa will be taking us through how measuring the silicone thickness and distribution of your injectable device with Bouncer can improve device manufacturing and the long-term stability of biologic formulations. And now, I'll hand it over to Lisa.
Yeah, thank you, Robin. And hello, everyone, and welcome to our seminar, Tackle Prefilled Syringe QC with Bouncer. I'm Lisa, and I'm application scientist at Unchained Labs based in Berlin and supporting our QC products. Here you can see our quality watchdogs, Hound and Bouncer. And we've recently done a few webinars about Hound. You can see here on the left. That's our particle identifier that combines microscopy with Raman and LIBS to quantify and identify particles in your samples. You can check out YouTube or our website if you're interested to see those. Today, I'm going to talk about Bouncer, our system to quantify the siliconization of your samples in syringes, vials, or cartridges. Syringes, vials, and cartridges are siliconized using different methods that impact the distribution of silicone on the inner surface and, in the end, the performance and quality of the device. When silicone is sprayed in, a fixed nozzle can be used or a dynamic nozzle can be used. And this has an impact on how the silicone is distributed on the inner surface. So if you use a dynamic one and the nozzle moves inside of the glass barrel, you usually get a more homogeneous distribution than just using a fixed one that's here in the lower part of the syringe. Another method is to use an emulsion of silicone that's sprayed in and then baked in so that you get a covalent linkage between the silicone and the glass, which usually leads to a thinner silicone layer and a more homogeneous silicone layer. And then, of course, you can vary the silicone load, the amount of silicone you spray in, which has an influence, of course, on the thickness of the silicone layer. But now, how does your coating impact the quality of your syringe? On this slide, you can see two examples of what consequences a poor coating, a poor silic coating can have. On the left, we see a graph showing typical force displacement curves that are measured when the plunger is pushed through the syringe or cartridge. And what you don't want to have when you do that is what you can see in a few graphs, that the applied force needs to get very high to move the plunger. This means actually that when you actually inject the product into a person, you will need a lot of force to move the plunger and do the injection, which means that this will become very uncomfortable for the person. Or if this is inside of a device that automatically injects the product, it can even mean that an injection is not possible if the force required to move the plunger is greater than the force that device can actually apply. Seeing this force increases for the bad examples here usually can have several reasons, but one of the most common one is that the siliconization of that sample was not good enough. That means maybe you have areas on the inner surface of the syringe where there is no silicone at all, or it's not enough silicone, and that's why the force you need to apply to inject gets very high. On the other hand, if you have a very inhomogeneous silicone layer or just too much silicone on the inner surface, you can also have impact on the product inside of your device. So on the right-hand side of this slide, we see another effect that can happen. And this is that the silicone migrates from the container surface into the product. So what we can see here is two images we took using our Hound instrument and analyzed the particles in a syringe or in a product that has been in a siliconized syringe. And what we see is we can detect silicone droplets in that syringe, and we can also see protein aggregation that might also have been induced by silicone droplets migrating into the product. So when you put a product into a siliconized syringe, what you want to know is if you have the right coating. On this picture, we see how silicone looks like when you just image the inner surface of a syringe using a microscope. And basically, this looks very similar as when you see an oil film on a surface or on a surface of water. So what you see is those colored fringes, and actually the color you see is dependent on the layer thickness of that oil film. In this case, it's the silicone oil film. But just from looking at it, how do you know if the distribution is good enough, and how do you learn about the distribution inside of your syringe? To figure that out, there are several traditional methods that have been used to characterize syringes and cartridges. One of them is measuring the force displacement that I've already shown in an earlier slide. So you measure the force required to move the plunger through the syringe. And the good thing about that is that this force is actually a direct parameter that tells you something about the quality of the syringe. So you immediately know if the force you require to do that movement is low enough so that your device can do that, or that it's comfortable for the patient to have the injection. On the other hand, that's a destructive method, so you can do that measurement, but then the sample is gone. Another common measurement or method to characterize siliconization in syringes is to extract the silicone and then just weigh, and in that way get a silicone mass that has been inside of the syringe. But in the same way as the force displacement measurement, this is a destructive measurement, and yeah, the sample is gone after that either. To visualize silicone distribution in a syringe, there are also techniques to like put some fine powder in the syringe, and this powder will also only stick to the surface where there is silicone. So we will see areas where we have silicone with a different contrast than the areas in the syringe where there is no silicone. But also this is a destructive method, and also it's just qualitative. So we won't know how much silicone there is, but just see if we have silicone on a position or not. And this is Bouncer. So with Bouncer, we have an option to analyze the silicone layer in a non-destructive way. And the information Bouncer can give you is the thickness. So it doesn't only measure if there is silicone on a position or not, but gives you a real quantitative thickness value. It performs that thickness measurement on a user-defined grid on the inner surface of the syringe, so that you can also get a distribution of silicone in the syringe. And it also calculates, based on these thickness measurements, the mass of silicone that is inside of the syringe. So you have quantitative numbers in the end that characterize your syringe silicone distribution in the syringe. To measure these values, Bouncer uses a microscope. You can see the microscope stand inside here. And we use two techniques to measure the thickness, which is white light reflectometry and laser interferometry. And I'll go into the details of that later. So let's first have a closer look how the samples are loaded in Bouncer. So here we can see a syringe loaded on the sample holder inside of the instrument. And the sample holder basically is two barrels that can be rotated so that we can look at that syringe from several angles. That whole holder is placed on a microscopic stage that can move in X, Y, and Z. So what happens during a measurement is, first thing, we move the syringe to a starting point so that we look at this, the ridge of the syringe close to the finger flange. Then the stage will move the syringe in X direction, which is along the axis of the syringe. And it will measure the thickness on a user-defined number of positions on the ridge of the syringe. When we have measured that whole line along the syringe, we can rotate the syringe by a user-defined angle and then measure the next line, so with a different angle. We will do that for a few lines, so you can measure up to 36, and then you have all the layer thicknesses and all the defined positions in the measurement. And thus get a distribution of silicone inside the syringe. The system can measure different types of samples. You can see here, so we measure syringes, cartridges, or vials that have dimensions in the limit stated here. So the measurement length can be up to 90 millimeter, and the system can handle diameters between 6 and 48 millimeters. The only other requirement for the sample that it's the barrel material is homogeneous and needs to be transparent, because we of course have to look through the glass barrel material to see the silicone layer. So here's a bit more detail about how we actually measure the layer thickness on all the positions the system evaluates. So Bouncer actually uses a combination of two techniques. One is white light reflectometry and one is laser interferometry. Both basically use interference from light that is reflected at two different interfaces we can see here in that sketch. So one interface is the boundary between glass and silicone, and the other one is the one between silicone and air. And those, the light reflected from both of those interfaces interferes, and we use that interference to evaluate the layer thickness. So for white light reflectometry, what we basically do is we, as the name says, we illuminate the sample with white light and measure the spectrum that's coming back. And remember the picture I showed you before where you can see the silicone as colored fringes. Basically what we do with white light reflectometry is we measure the spectrum, that is the color information reflected back, and from that color information we can conclude back to the layer thickness we have there. This technique works with silicone layers down to 80 nanometers. Which is working well alone for like most sprayed on siliconized syringes. But especially if we do want to measure baked in siliconized samples, those layers are oftentimes much thinner than 80 nanometers. And to be able to also measure those, we added laser interferometry as a second technique, and combining both of them, we can measure layer thicknesses from 20 nanometers up to several micrometer thickness. This graph shows how these two techniques are combined. So what we see here is one of the outputs Bouncer gives us for every line it measures. So it's showing the layer thickness versus the distance from a start point we choose on the sample. Start point is usually close to the finger flange. And we can see each of those bars is a measured layer thickness on the positions the system evaluates. And you can see it's a nice distribution along the ridge of the syringe or the length of the syringe, and all the values that are bigger than 80 nanometers come from white light reflectometry, and the ones lower from laser interferometry, and Bouncer automatically already combines those values to show all the results in one graph. Usually you set the system up to measure several angles across the circumference of the syringe. Here is an example where you can see how this can be distributed, usually equal distribution around that circle. And then when you measure several angles, the system will create something like this heat map. So you can see a representation of the layer thickness inside of the syringe, graphically as a map where you can where the height of the silicone layer is color coded. And using these silicone height maps, you can see things like, is my distribution homogeneous, or do I have silicone everywhere on the whole length of the syringe, or are there areas where I didn't get silicone? And in this particular example, one thing you could probably detect here is that the silicone accumulated in we see some accumulation only on 1 or 2 angles we measured. This could probably be caused by storing the syringe horizontally, so that all the silicone fluid moved down to the bottom of the syringe. Yeah, and then Bouncer will also calculate a silicone mass for the silicone inside of the sample. And it will use this formula. Basically, this is the area of the cylinder surface of the inner surface of the syringe multiplied by the average of layer thickness that has been measured and multiplied by the specific gravity of silicone. And you will have that value reported in a report. So what are people using Bouncer for? Here is one example that's referencing a publication you can see here, where they tried several methods for siliconization. So you can see FN is a fixed nozzle, DN is dynamic nozzle. And they correlated the measurements they got from Bouncer here on the left-hand side with the amounts of particles they then found in the samples that have been stored in the syringes that have been siliconized by these techniques. So let's, for example, have a look at the blue data. For the blue data, we see this was siliconized using a fixed nozzle. When we see here the mean silicone layer thickness versus the distance from the flange, we see it's a very inhomogeneous distribution. There is quite a lot of silicone in that sample, so the thickness here close to the flange is kind of 800 to 900 nanometers. And then it gets very thin, closer to the tip of the syringe. And when we look at the particle numbers found in those samples, we see that this coating has produced the most particles in the sample. When we compare with the other techniques used for siliconization, those produced a little bit less particles, and we can also see they seem to be more homogeneous across or along the length of the syringe. Another application for Bouncer is to use it to check the quality of the siliconized syringes provided by your suppliers. So you can find the ones with a good siliconization, and more importantly, the ones where siliconization doesn't fulfill your requirements. So on this slide, we have 2 examples. The syringe investigated here on the top we see that along the length of the syringe, we have silicone everywhere. And you could conclude that for this one, the risk is pretty low that you would need a huge force to move the plunger through this syringe. Another syringe was tested, and this one's here below, where we can see that we have some silicone, but only close to the finger flange, and then there is large areas of the surface where we don't detect any silicone at all. So for this one, probably the risk would be pretty high that you would need a huge force to move the plunger through the syringe. So before we go into one other case study in more detail, this is a slide summing up what Bouncer can do, where it's applied for which applications. So you can use it to identify the ideal coating to, in case you have a siliconization process you want to optimize, maybe optimize the amount of silicone you want to use, or the settings for the nozzles. You can vary those and use Bouncer to figure out which ones were the ones giving you the best siliconization. You can use it for QC of incoming devices. Then another example is to study the interaction between the device and the drug. And this example, and this will be covered in the case study. A lot of people correlate the siliconization they measure with Bouncer with the force displacement measurements, so that you can make a prediction from the Bouncer measurements which devices would work well, or wouldn't require too high forces. And you can also study changes over time, like from storing the syringes, etc. So let's have a look at that case study now. The case study I want to present today is about the effect of syringe storage on the siliconization. And here you can see the study conditions. So what we tested for this study is sprayed on siliconized syringes. They were filled with human IgG in a concentration of 10 mg/ml in PBS buffer. And after filling them with the protein, we tested 3 different storage conditions. So one was storing those syringes for 16 hours at 4 degrees Celsius. Another set of syringes was stored at 40 degrees Celsius for 16 hours. And the third one was mixed for 3 hours at 20 degrees Celsius. So for each of those sets, we did three replicates. The experimental setup was as follows. So before we actually filled the syringes, we did an initial silicone measurement using Bouncer. Then they were filled with the protein solution, then incubated or stressed according to the 3 different conditions I just explained. Then the solution was removed by decanting, because we only analyze the syringes when they are not filled with product. Before we measured them, they were desiccated for 48 hours to dry, so that we don't have any effect from any liquid that's still sticking to the silicone. And then we measured the silicone after drying. Before I go into the details of the results, let's have a look at what we actually are looking at. So we kind of see again those heat maps Bouncer creates, where the area we see represents the inner surface of the syringe, and the color represents the layer thickness. So you can see when you look at the color code, blue means rather thinner layers in the range of 40 to 60 nanometers, green the rather thicker layers in the range of a few hundred nanometers. And then we go from bottom to top here in this image. We move actually from finger flange along the syringe in the direction of the tip of the syringe. And in the x-axis, we have the different rotation angles. So in our case, we measured 6 different angles at 0, 60, etc. degrees. Yeah. And then the other information we will see is the average of the layer thicknesses that have been measured by bouncers. So this is averaging all measurement positions. And then from that, the system will also calculate the silicone mass using the formula I showed before. So let's move into the results. First thing we did is PBS control. So in this case, the syringe was just filled with PBS, stored at 4 degrees for 16 hours. And when we compare those silicon height maps or heat maps before and after that storing for 16 hours, we see that there is basically no change. So the siliconization is very homogeneous in the beginning, and it stays like that even after storing. And when we look at the values for mean thickness and silicone mass, those basically didn't change. So what happens when we fill it with protein? In this case, we filled it with a 10 mg per ml IgG, stored it for 16 hours at 4 degrees. And here we can see a slight effect, actually. So we can see when we look at the right picture, there is a few more blue spots in the siliconization. That means that some of that, in some parts of the area, the silicone layer got thinner. So some of the silicone disappeared from the layer. And of course, the silicone didn't just disappear, but rather it moved from the glass surface into the product, which can also be seen by that mean thickness and silicone mass values, of course. What happens when we apply mixing stress? So we can see that in this. Let's have a look again at the initial and final heat maps of the silicone heights. Same here. So we lose some silicone from the glass surface into the product. And it's a little bit more than when we just store it at a cool temperature. The most silicone losses we see when we actually store the samples at heated temperature. So this was stored at 40 degrees for 16 hours. And in this case, again, we see silicone loss. And when we look at the numbers here, we can see that the silicone mass is almost half of it, of the number it was before we did that stressing step. Here's a summary showing silicone masses measured for all of those 3 stress conditions. And we can see that, again, heat led to the greatest silicone loss, but also we can see some silicone loss for all the 3 stressing conditions. So using this technique on bouncer, we can learn about silicone interaction with the product under different conditions and migration of silicone into the product. So bouncer is a great tool that complements methods that are used to investigate performance of syringes and drug quality. For example, force displacement measurements are a very common way you can use to find out if your performance requirements for the syringe are satisfied by measuring the force. If you combine it with the information bouncer gives you, you can also get answers about how this performance is related to the silicone coating and how the coating impacts that performance. If you're concerned about drug quality, Hound is a great tool for particle counting and identification of particles in your product. And you can use it to figure out about your drug product quality. And combining this Hound with the information bouncer gives you, you can actually find out if the drug product quality issues you might see using Hound could be caused by a bad siliconization, where a bouncer can give you information about that. for example, if some silicone migrated into the product and caused that aggregation of proteins. To sum up, using Bouncer, you can make sure that the siliconization of samples fulfills the requirements needed for your devices. And ensuring the performance of syringes and devices by having a good quality of siliconization is important, especially when looking at examples like this, where you have injections into the eye. In those cases, you surely don't want to have the situation that a huge force is required to do the injection. With this, I'd like to thank you for joining our webinar today. I'm happy to answer any questions you might have. And I hand over again to Robin to moderate the Q&A session. Thanks.
Thank you, Lisa, for that great overview of how using Bouncer to measure silicon thickness and distribution can ensure your coding of your devices is just right. We have some great questions that have come in and already been submitted. As a reminder, you can still submit questions using that Q&A button on the Zoom navigation bar at either the top or bottom of your screen. So to get started, Lisa, the first question is, can you see silicon droplets and the distribution of silicon?
Yeah, so Bouncer definitely measures the distribution of silicone on the inner surface of the syringe. You saw those heat maps where you can see if this silicone accumulates maybe close to the finger flange or close to the tip of the syringe, or maybe on a certain angle because it moved down during storage. So you really get a quantitative measure of the silicone thickness and distribution. You can also see droplets. So what we do, we use a camera that actually images the silicone, like in the image you saw on one of the slides. And on those images, you can also actually see those droplets, and you save those images if you require them. But you actually have a more quantitative information with the actual thickness values you get from Bouncer.
Awesome, thank you. What kind of controls or references are used?
Yeah, so first thing to like check instrument performance, we have certain standards. So those are coded half cube shaped half barrels, and they have a coating with a specified thickness. So we have a certifier that certifies the thickness of those, and we have them in a certain range covering the low end thicknesses we can measure and going to several hundreds of nanometers. And yeah, using those certified standards, we can make sure that Bouncer is giving us the correct thicknesses. Then for having a negative control with no silicone, when you do a measurement, you always need a syringe or a cartridge of the same geometry to tell the system that's my reference. This is the spectrum you measure when there is no silicone or the reflected laser intensity. So you always have to do that blank measurement first with a non-siliconized syringe or cartridge.
Lisa, can you please describe the sample preparation process?
Sure. If you have a syringe that's siliconized but doesn't contain any product, there is actually no sample preparation. You only need, as I just described, a reference sample that's non-siliconized, measure that reference value, and then you can just put your sample on the Bouncer and measure the siliconization. If you use, or if you want to measure siliconization on a sample that's filled with a product, what you need to do first is empty that sample. So you decant the syringe, and then it's like I described in the last case study. So after decanting, we need a drying step to make sure that any liquid that's sticking or that's still in the syringe doesn't affect our measurements. So we usually put it into a desiccator, and then after that, you can also just measure, no other sample preparation.
Lisa, a couple questions have come in about if measurement is possible with material different from glass. Can you address that, and specifically for plastics and clear polypropylene?
Yes, we can measure other syringes of other materials too. It has to be a transparent material, so we need a certain level of transparency, and also it should be rather homogeneous. We have used the bouncer routinely to measure COC syringes, for example. For polypropylene, I think it depends a bit on how transparent that material is.
What are the minimum and maximum syringe sizes that bouncer can measure?
Yeah, so the minimum diameter it can deal with is 6 millimeters, and the maximum diameter up to 48 millimeters. And the size, so the length it can measure is up to 90 millimeters.
Okay, and is that for only syringes, or can you measure and analyze other siliconized containers, for example, vials?
You can also measure vials or cartridges, yes.
And how long does it take to analyze each of these syringes?
It depends a bit. So I think I mentioned a few times that the user sets up the number of points per line and also the number of angles that should be measured. And then also it depends if you use both techniques we have in that instrument. So remember I mentioned white light reflectometry and laser interferometry, and you can use both for any measurement. But sometimes, especially if you expect that you have a rather thick siliconization, you would sometimes decide to only use white light reflectometry because that's the faster technique. So for a standard measurement, let's say with 6 lines using 6 lines or 6 angles using white light reflectometry, this would be a few minutes. So let's say 5 minutes typically. If you use laser interferometry, it would typically be about 20 minutes per sample.
Is there a lab that you can send samples to pay for analysis there?
Yes, there is. We have a contract testing lab in Belgium, in Ghent. And I'm sure our sales team is happy to get in contact with you to figure out what you want us to do there. But yeah, we routinely measure siliconization of syringes and cartridges there using our bouncer systems.
Is the instrument compliant with 21 CFR Part 11 and FDA data integrity requirements?
Yeah, bouncer is compatible with the CFR Part 11, so it has audit trail, user logins, etc. Yes.
And Lisa, how does bouncer compare to other methods of characterizing silicone layers?
Yeah, if you compare it to those techniques for silicone visualization, where you put a fine powder into the sample, this is qualitative. Bouncer is actually the only method that really measures quantitatively the layer thickness and thickness distribution inside of the syringe. If you compare it to force displacement measurements, that one is also destructive. Bouncer is non-destructive. Same for extraction. So compared to all those traditional methods, we are non-destructive, so you can still work with the sample afterwards. And we are quantitative, as this bouncer is the only instrument giving you quantitative layer thickness values.
Awesome. Well, it looks like that's all the questions we have time for today. So thank you for answering all these great questions, Lisa. And thank you for that great presentation today. I also want to thank all of you who joined us live today. If you would like to have a deeper conversation with our sales team, please do get in touch with us. Our team would love to connect with you over a Zoom meeting. And any questions that we didn't have time to get to, we'll reach out to you and discuss those with you as well. Thank you for attending our virtual seminar, and I hope you have a great rest of your day.
Thank you.